Hi, Deborah.
Hello.
I think me and you are the only one here right now. Yeah.
Okay.
Oh, there's somebody else. See, waiting room. We got Alexis and Tiara. Who's a Clemson fan? You are? Did one of your parents go to Clemson?
No, I grew up in Charleston and knew a lot of people who went there.
Oh, okay. I have friends that grew up in North Carolina that are big Clemson fans too.
Yeah.
So, yeah. But you guys have lots to cheer about lately.
Yeah.
Yeah. Wonderful. They're gonna be crushed if they don't get to have football this fall. I'm telling you.
Yeah, I know. Yeah.
That's bad. Okay, let's see. We're waiting for Dion. Let me get.
She's having trouble logging on.
Is she? Okay.
Yeah, she just texted me saying is Zoom letting me on.
Okay. Did she have to put the password in? She's not in my waiting room yet. So text her back, Alexis, and tell her to keep trying.
All right.
So, did you get your hair done? I can't tell.
No, I just did it. You know, it's Monday when the magic's gonna happen. The magic and the pain. Because I'm super tender-headed.
All right. Well, I don't know what to tell them. She might be able to hear if she logs on her phone, but I don't know. She won't be able to see anything, so that's kind of not good.
It's my first class today.
Really? Did you sleep late?
Well, you know, I overslept because I was watching this documentary about R. Kelly. And, you know, it was part 2. And I had to watch it. I went to bed like 4. And I was like, I can get up. And I ain't hear it.
All right.
My next class, we canceled it.
I see Tiara from her nose up. And she's got a reflection of her computer screen in her glasses. That's good. I mean, she looks like an alien being. But anyway, so I can't see if she's smiling or frowning out here. So
I think she's laughing.
Maybe that's why she wants me to
I honestly have no expression on my face right now.
Okay.
Tell me why Walker was playing that rap music to talk about I know what 420 is and stuff like that.
Yeah, he was doing too much this morning. I'm sorry. He wasted 30 minutes on nothing.
What were you doing?
We had a review in chemistry this morning at 8 o'clock, and he wasted 30 minutes on nothing. I was just sitting there looking at the walls for 30 minutes.
Okay, well, I'm going to try really hard not to waste your time today, okay?
Because everybody wasted my time this morning.
I'm under a big pressure here. Okay, all right. Now let me bring up something here then, see what I got. All right, so if you look at your assignment sheet, I had something, there were sort of 2 days on absolute convergence and conditional convergence, and I did the ratio test yesterday. So we really hadn't gotten a chance to practice the ratio test very much, or a lot of these things. So I want to do some practice problems first on the stuff that we've got, and then I want to move on maybe to just introduce, and I'll continue it Monday, to something called power series. And power series are sort of an extension of all the kinds of series we've had. But instead of having numbers in the series, we have variables in the series. And you'll see how that's powerful. That's why it's called a power series. We'll see how it works out when we get to that. But let me remind you, number one, of the ratio test, and then I'm going to see if you've got any homework questions. And if you don't, well, I'm going to provide you with some things to do this morning. Well, it's not morning anymore. It's afternoon. Okay. So here's what the ratio test said. We were talking about absolute convergence, conditional convergence, and just diverging. Those are things you talk about when you have negative terms in your series. I'm going to lay out kind of a flow chart for you guys later, how to think about all this, because it's a lot of different terms. And we also learned that if something absolutely converged, then it converged. Well, this ratio test right here, this thing called the ratio test, is a test for absolute convergence. If you can use it and it satisfies it, if the limit you get from this test is less than 1, then your series is absolutely convergent. If it goes to infinity, it is not absolutely convergent, okay? So if it goes, or if it's bigger than 1, okay? So here's what the test said. Let's just review what the test said. What we do to use the this test is we take the limit as n goes to infinity of the absolute value. That would knock out any negative terms we had there. So you could use this. Oh, there she is. Hang on, guys. Let me get her in before she pops out again. I'm on, Dion.
This is apple juice.
You have to keep telling me what you're drinking because you think I think it's wine or beer?
Yeah, I don't want nobody to think I'm illegally drinking. This is
No.
this is apple juice.
Okay, all right. Last time you told me that it looked red, so I thought, well, she must think I think it's wine. Okay, all right. There's Dion. Okay.
So fancy.
What happened? Was your internet not letting you in, Dion?
It didn't let, it just said it stayed on the screen. It didn't let me put the password in. So I had to go back out and redo everything.
Okay, I had that trouble yesterday too, and I had to put the password back in too. And I thought my password was already cooked into my account, but I guess not. Anyway, okay, so yesterday we did this ratio test, which was a test for absolute convergence. And what we did was we took a look at the limit as n goes to infinity, the absolute value of the n plus first term over the nth term. If we got a limit that was less than 1, we could say the series is absolutely convergent, okay? And absolute convergence implies convergence. So this works not only for negative terms with negative, series with negative terms in them, it works for any series. It'll tell you that the thing absolutely converges and therefore converges. If the limit is greater than 1, or if it goes to infinity, the series is gonna diverge. If L equal 1, the test is inconclusive, you gotta look at something else. So what I'd like to do is just do a couple more of these things, and I did a couple in class, so I'll just let those ride. One thing I did say was that I will tell you that if I ever see factorial in something, even if it's an alternating series, I'm gonna go for the ratio test. Because in the alternating series, you have to show that this thing is decreasing. This will certainly go to 0 because if you look at it, and again, because you may not know much about factorials grow really quickly. And powers of 3 grow less quickly. So this limit eventually is gonna go to 0. If you got your calculators with you, I'll show you what I mean about factorials. So let me show you how to find factorials on your calculator, and then we'll look at something that's true about factorials. Suppose I want to find 5 factorial. Okay, so if you're on the calculator and you want to find 5 factorial, go to your home screen and put in 5. Okay, if you want to find out where the factorial key is, you hit the math key, which is in the first column there. Hit the math key, go over to PRB. There are you can't see it, but there are menus across the top, and it says Math, NUM, CPS, PRB. PRB stands for probability, okay? And under that is a whole list of things that have to do with probability. And factorials turn out to be really important in probability. But if you go down, at least on my calculator, it's number 4. You'll see the exclamation point, okay? So if you got your calculator with you, again, you write the number of the thing you want, okay? That's 5. If you want a factorial, hit Math, scroll over to PRB, and then go down to that factorial and hit Enter. And it'll enter an exclamation point or a factorial mark after the 5. So then when you hit Enter again, it'll tell you that 5 factorial is 120. So remember what 5 factorial was? It was 5, 4, 3, 2, 1. Okay? So that's what 5 factorial is. So let's look at something else. Let's look at 20 factorial. I don't enter 20 on your home screen, and then go Math, over to PRB, down to factorial. You should see 20 factorial on your screen. Hit it. What kind of number you guys getting? Somebody tell me what you see.
Scientific.
Do you see 2.329 blah 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 E18?
Mm-hmm.
Yeah.
You guys do science. You know what E18 means? That's just scientific notation. It basically means times 10 to the 18th power. So that's a number, you would move that decimal over 18 times, which you can see is going to be a big number. Okay, so I got up to 20 factorial and I had that big a number. Now, something that's really interesting on the calculator, your calculator will hold something, most calculators of the 84 genre will hold something that's times 10 to the 99th power. In other words, it'll hold something as big as something with 99 zeros in it, which is pretty big. Suppose I put in 68 factorial, guys. So put in 68, and let's go back to math, cross to prob, PRB, hit factorial, and then enter it. What I see a number, what's the exponential? What's the end of the exponential on that one, guys? Times 10 to the what power? What are you seeing?
96.
96. That's a number with, you've moved that decimal over 96 decimal places, okay? Hit 69 factorial. All right, so if I hit 69, math, prob, I go down, factorial, hit factorial, I've got times 10 to the 98th power. Okay, now I'm gonna go for 70. You know what I'm trying to do here, probably.
Yeah, it's overflow.
Okay, so when I get to 70, I go to probability, factorial. It gives me an overflow error. It will not hold a number as big as 70 factorial. So 3 to the 70th power isn't going to hold a candle to 70 factorial. Okay, so this thing definitely is going to 0. But you know what? I don't know how to use L'Hopital's rule on that. I just know it's going to happen because I know how these things behave. Because you know, that's infinity and that's infinity, but I don't know how to differentiate n factorial. We've never talked about finding the derivative of n factorial. We won't talk about finding the derivative of n factorial, but it does go to 0. But it leaves me with a little problem that, well, you know, if I can't really say, if I just say I have a feeling it goes to 0, that's not quite good enough. So what we would do is use the ratio test on this thing, okay? And that's what we did in what we did yesterday, okay? Let's see, sorry, my screen's blanking out. I'm talking so long. If I went down to sort of review what it said, you look at the limit as n goes to factorial, you put in 3 to the n plus 1 over n plus 1 factorial. That's my an plus 1. On the bottom is 3n over n factorial. That's my an. Invert and multiply. We talked about how these factorials would cancel out with each other, leaving you with just n plus 1. 3 to the n plus 1 over 3 to the n. The 3 to the n's cancel out, and you just got a 3 left. So now that limit goes to 0. According to the ratio test, 0 is a constant less than 1. The series absolutely converges. And if the series absolutely converges, the original series converges. Okay, but you'll say it's absolutely convergent. Okay, so that's essentially what we did yesterday. Let me just pick out another one. I want to show you some problems in the book that we can use the ratio test on. I've got, if you will look, and you can write this down if you don't have it, if you don't have your book close by, but just as in that chapter on integrals, where we had a bunch of integrals to work at the end of the chapter, in the chapter review, there are a bunch of integrals to work at the end of this chapter. And that page is, where'd it go? I've already passed it. That page is page 599. So I want to look right now at 599, and then we're going to look back at your homework and see if you see any there. Who's got a book? Raise your hand if you can see your book. Okay, all right, everybody can see the book. Okay, good. So I want you to look on page 599 and pick out the first one you see, starting with number 7. pick out the first one you
said
see.
page 599.
Yeah, 599.
Oh my God.
Not at the end of this chapter. That's just at the end. That's just review problems at the end of the chapter. I don't
Uh-oh.
care if it's the first one you see, but I want you to pick out one that's got factorials in it.
13.
Okay, 13 looks like the first one there. So let's look at 13 and see if we can use this. We should be able to use the ratio test on this one. In 13, it says the limit from n equal 1 to infinity of n factorial over log n plus 1. Over log n plus 1. Now, I've got a guess about this one, but we're going to use a ratio test to see if my guess is right. I think this thing's going to diverge. Because I think if you looked at the successive sums of these things, this n factorial right here is going to grow a lot faster than that log, which means it's just, things are just going to get bigger and bigger that you add on to that sequence of partial sums. But let's use the ratio test on it and see what happens. The ratio test says here that the limit, we're going to look at the limit as n goes to infinity. We don't have any negative terms in this, so it's kind of a moot point to use the absolute value, but typically we use the absolute value. If there are negative values in it, that gets rid of them. So what we put in the top, actually I'm going to get rid of them because we don't need the absolute value in this one because they're all positive terms. What I'm going to put in the top is n plus 1 factorial over the natural log of n plus 1 plus 1. So you see what I did? I put, that's a sub n plus 1, okay? And then in the bottom, I'm going to put n factorial over log n plus 1.
This is a lot.
Okay? So this is my an plus 1. That's my an. Now I'm going to simplify it. If I invert and multiply, I'm going to get the limit as n goes to infinity of n plus 1 factorial over the natural log of 2. No, sorry, natural log of n plus 2. Sorry about that. Get rid of that. Natural log of n plus 2. Invert and multiply, the n factorial ends up on the bottom, and the log of n plus 1 ends up on the top. Okay? So I wind up with n factorial over n factorial. Everything cancels out after n. It's n times n minus 1 and so on. That's what we talked about yesterday. If you don't get that, you need to let me know. That's going to be an n plus 1. This is going to be a log n plus 1 over log n plus 2. Okay, so now I've simplified it as much as I can. I don't think I've made any mistakes. Is everybody okay with the n plus 1 factorial over the n factorial? Everything but n on cancels out, so you got that n plus 1 left. Now I need to know what happens as n goes to infinity. There are a couple things I can do here. It looks a little bit messy, but I know that this thing right here, if n gets bigger and bigger, that's getting bigger and bigger. The log of something bigger and bigger is bigger and bigger. And the log of something down here is bigger and bigger. What form does this end up in, guys, if you just look at the log as n goes to infinity?
Infinity over infinity.
Mm-hmm. It's infinity over infinity. That makes me think, well, you know what? I probably want to use a L'Hopital's rule on this thing. So let's use L'Hopital's rule. I'll have the limit as n goes to infinity. I'm going to have to use the product rule on this, but it won't be too bad. It'll be n plus 1 times the derivative of log n plus 1. Well, that's just 1 over n plus 1 times 1, plus the log of n plus 1, the derivative of that times the derivative of that, which is 1. And what's the derivative of the log of n plus 2, guys?
1 over n plus 2.
Yeah, 1 over n plus 2. All right, I need to clean it up a little bit so I can see what the limit is. See if it helps. See if that helped me. That's the limit. As n goes to infinity, that goes, so I get 1 plus log of n plus 1. All right, I'm going to invert and multiply now times this thing, n plus 2. Okay, if I got it right, 1 plus log n plus 1. You could distribute that n plus 2 if you wanted to. It'd be n plus 2 plus n plus 2 times log n plus 1. But no matter what you do here, guys, where's n going? Where's n plus 2 going as n goes to infinity? Infinity. This is going to infinity. Log's getting bigger and bigger. You got infinity plus infinity. That thing is going to infinity. And what the ratio test says is that it diverges if it goes to infinity. Okay? So that thing diverges by the ratio test. Okay? So that's how we use the ratio test. And we also use it on things that have negative terms in them. Let me find another one here. Look at, trying to find one. Whose dog's barking?
Man, mine, I wish I had a dog.
All right, guys, I'm going to look at number 24 on that page. Let's look at 24, because it's got some negative terms in it. I do need to look at absolute value for that. So let's look at 24. So 24 looks like this. The sum from n equal 1 to infinity of minus 1 to the nth, 2n plus 3 over n factorial.
I have a question.
Yes, ma'am.
So when people are writing these problems,
Mm-hmm.
what makes them write them the way they write them? You know what I'm saying?
Well, they do come from some applications, I will tell you that, but it's hard for me to explain to you what the applications are that come from. But when they're writing them for a calculus book like this, they're trying to write problems in a section that give you a wide variety of ways you can do it, okay? And so, for instance, in this particular chapter, you've done comparison tests, you've done this ratio test, you've done geometric series. This is not a geometric series. You've done all kinds of things. So they mix them all up so you can figure out for yourself what's the best way to do a problem. Okay? So, does this problem have negative terms in it, guys?
Yes.
Yes. So you're going to have to say either absolutely converges, conditionally converges, or diverges. Now, the ratio test is, as far as that, making a decision on that goes, the best thing you can do is use the ratio test because it tells you about absolute convergence. If it works, if it passes the ratio test, in other words, L is whatever, less than 1, then you're going to get something that is absolutely convergent, okay? Now, so which basically means that this part converges and so does this whole thing converges and so does its absolute value. So it's absolutely convergent. So here's what I'm going to do on this one. I'm going to say the limit as n goes to infinity of the, now I do need the absolute value, guys. And I'll carry that through for a second. I didn't do that yesterday, but I'm going to add n plus 1 there, okay? And this will be 2 times n plus 1 plus 3 over n factorial. Now, a lot of times I'll just cut to the chase here, guys. I know I'm going to divide by this thing right here with the n in it. And I know ultimately I'm going to invert and multiply. So sometimes I'll just do all that in one step. Something didn't write out very well. This was n plus 1 factorial right there. So dividing by that thing right there, the an term means I'm going to invert and multiply. Okay. So actually, and down here, I might have minus 1 to the nth because that's part of the n term. But it doesn't matter here. That'll be -1 to the first. And once we take the absolute value of that's just going to be 1. So those are going to, that's going to go. That's going to be a
So anytime we have that, we can just go ahead and like take that out.
yeah, you can do that. Is there any time when
The
that
top
would
part.
be a problem?
It-
I don't think there's any time that would be a problem because we're taking the absolute value of all the terms. So when I keep going, try to take the limit of this thing.
Dion, you trying to say something?
Yeah.
Oh, okay.
What were you trying to say, Dion?
How'd you get that part up there? The
This part-
two.
This part right here,
Yeah.
that part, the limit, the ratio test says you want to look at the limit of an plus 1 over an. So an plus 1, this is an for the problem. An plus 1, everywhere there's an n, you put in an n plus 1.
Oh, okay.
Okay, that's all it is. And then when you divide by the other thing, it gets inverted. Okay. So what I've got is 2n plus 2 plus 3, which is 2n plus 5. N factorial over n plus 1 factorial is n plus 1. And then also down below, then I've got a 2n plus 3 there. Okay, so that was that. What
Okay.
canceled, I got the n plus 1, and then up top I got 2n plus 2 plus 3 plus was 2n plus 5.
Okay.
So, you know, how far you go here just depends on how confident you are, I guess. If you look at this thing, you'll have 2n plus 5. If you multiply this out, you'd have 2n squared plus 5n plus 3. You pretty much know what that's going to do. Now, all of these are positive terms. I would encourage you to keep the absolute value because there's something late. You really don't need it here because these are all positive things. But later on, we're going to have variables in here, and we're not going to know whether they're positive or negative. So I'm going to sort of encourage you to leave that in there. But tell me what that goes to right there.
0.
Goes to 0 because the power down here is higher than the power there. So that thing, whole thing is going to 0. 0 is less than 1. So by the ratio test, this thing absolutely converges. If I can't spell it. Absolutely converges.
When we say like it absolutely converges, are we talking about something like a graph or something like?
No, not really. We're talking about the fact that if you looked at the terms of this thing and you made all the negatives, all the ones that were negative positive, not only will this one converge, but the ones that have all the positives in them will also converge. It's just okay. Yeah. All right. So that's what we learned yesterday. Now let me sort of, I want to show you kind of I like to think about this sometimes as a flow chart. Okay, guys. So here's what I think about when I think about all the stuff we've learned here. You've got some series up there, whatever, blah blah blah, an. Okay. It maybe all it has is positive terms in it. Now, if it's got only positive terms in it, then I can use a couple of things. The first thing I'm probably going to do always is check to see if the limit as n goes to infinity of an is equal to 0. Because if it doesn't go to 0, I can stop and say that thing diverges. Remember, that's the nth term divergence test. Okay? So that's probably the first thing I'm going to do. The next thing I'm going to do, if it's all positive terms, I've got a lot of tests I can use. Maybe it's a geometric series. And geometric series, by the way, don't always have positive terms in them, but they often have only positive terms. I can use a basic comparison test where I just compared one to see if something bigger diverged or something less than something diverged. I could use the limit comparison test. All those we've kind of looked at. I could look and see if it was a p-series or could be compared to a p-series. All right. I could see if it was telescoping. Those are kind of, you'll recognize those. So I could see if it was telescoping. All right. I could see if it was a p-series. Finally, I could also use the ratio test on it. All right, whoops. I could use the ratio test. So, and if I look at all of those, that thing either diverges or converges. There's no absolute convergence here because it doesn't matter about the absolute value because it's got all positive terms in it. All right, so it either converges or diverges. Now that's if it's all positive terms. Converges or diverges. Okay, well, heck. Okay. All right, now, if it's got negative terms in it, so suppose it has negative terms. If it's got negative terms in it, it might be alternating. Now we saw that negative terms didn't always mean it was alternating. Yesterday we had one that was 2 pluses and 2 minuses and 2 pluses and so on. If it's alternating, I might be able to use the alternating series test. I have to show that AN goes to 0 and I have to show that things decreasing. The tough thing about this might sometimes be, well, both of those, but it might be hard to show it's decreasing. Sometimes with factorial, it's hard to show well, you can sort of feel like the limit's going to go to 0, but it's hard to show. So you could do that. You could use the ratio test. And in the ratio test, it doesn't really matter whether it's alternating or not, as long as it doesn't even have to have negative terms, okay? Because you can use the ratio test in either situation. You can use a ratio test where it has negative or where it has positive. You might be able to use a basic comparison test or maybe some kind of comparison test. Now, that's not immediately obvious, but I'll show you where that might happen. Remember we had one that looked like this, the sine n over n squared, n equal 1 to infinity. That thing right there has some negative terms in it, but I'm not sure at all it alternates. But if I look at the absolute value of that thing, I would have that series was certainly less than 1 over n squared. Okay, if I were to look at that in absolute value. Okay, and remember, if it absolutely converges, then it converges. So I'm good with that. This is a P series that converges. It dominates that. Therefore, that thing is going to be absolutely convergent. Actually, I would show that you would call that absolute convergence. So long story short, if it's got negative terms in it, the possibility for your answers is conditional convergence, conditional convergence. That means it converged, but its absolute value didn't. So look at the definition of that. Your book will write probably CC for that. Conditional convergence, absolute convergence, or divergence. Okay. So that's where you've got to use, if you have negative terms, you have to say one of these things. Okay. If you don't have any negative terms, converges and diverges are fine because the absolute value of something of all positives is just the same thing. Okay. So, what I want you to do for the weekend, I'm going to show you one other thing as sort of an introduction to what we're going to do next week. But what I want you to do for the weekend is look on, I think I put the homework on this stuff on Wednesday. And then Thursday it said, we'll continue the homework. Look at the homework I assigned on Wednesday. I may not get far enough today to do much homework on the power series stuff, but I want to introduce it. So do as many as you can on the homework that was listed under Wednesday and repeated for Thursday. So it's got all of these tests with it. I want to say one more thing about factorial though, in case you run into it. I mean, suppose you had something that was 2n plus 1 factorial and 2n factorial. And I ask you to, actually, and I'm putting that in parentheses there, and I ask you to simplify that. If I ask you to simplify that, it kind of works the same way, guys. Actually, I'm going to change this to 2n plus 2. 2n plus 2. what factorial does is it starts with the number. So this will start with 2n plus 2, and then it goes to one less. One less will be 2n plus 1. The next one less will be 2n. The next one will be 2n minus 1, and so on until you get down to 3, 2, 1. So you start with what was factorial, you take away 1 every time, and you look at that. If I were to look at the top, it would start at 2n. The next term would be 2n minus 1, and then 2n minus 2, and so on until I got down to 3, 2, 1. Now, what's going to cancel out in this, guys?
Sure, I don't know.
Yeah, 2n and on, because look, eventually they one of them sort of caught up with the other one, or this one was ahead of the other one, all right? And if it was ahead of it, that's going to cancel, the next one will cancel, and the 3 and the 2 and the 1 will cancel, and that will simplify into 2n plus 2 times 2n plus 1. So that's what's left after you cancel out all the things that get repeated, because eventually it's going to repeat. So example, suppose I said, I always like to do this to my finite math students. Suppose I said 100 factorial over 98 factorial. Now, I'm going to tell you what they do. They go to their calculator, even though I've told them 15 times that it ain't going to work. And they put in 100 factorial, and then they divide by 98 factorial. And what do you think happens on that calculator?
No, I just, I grabbed some.
The thing just crashes. You know why? Calculator can't handle that big, right? So here's what I tell them to do.
Funny.
What?
She laughing.
Who? Tiara's laughing. Why are you laughing, Tiara? But you know what? Tiara, tell me what would you do? Really, tell me what you would do with this thing, because it's not gonna work in the calculator. What's gonna cancel out, guys, when you look at this thing?
98.
Everything from 98 on, which is gonna leave you with what?
100 times 99.
100 times 99, okay?
I don't see how y'all see that.
Well, what does 100 factorial mean, Alexis? 100, 99, 98, 97, 96. That means 98, 97, 96. Everything from 98 on drops out. You're just left with 100 and 101.
What?
What?
See, I'm not gonna lie. I'm gonna do with them finite students. There, I'm gonna put in the calculator.
No, don't do that. Well, you do it if you want to. It ain't gonna help you any. Okay.
If I do 50 and 50 added together, that's.
I didn't tell you anything about splitting it up. That doesn't work. 50 factorial plus 50 factorial is not as big as 100 factorial, by the way. But you might want to check that out.
Right.
It might be hard to check. Because 2 times 50 factorial is less than 100 factorial, because you think about it. That's a good thing to think about. Think about that. But anyway.
Well, I still don't understand that. Like,
Okay, look at this.
I don't want to.
All right, look.
I should, but I don't.
No, you tell me what I told you 100 factorial was. It's 100 times 99 times 98 times 97. Now, I don't want to be here till tomorrow afternoon, so I know eventually this is going to end with 3, 2, 1, right? That's what I told you factorial was, right?
Yes.
Say right. Yes, you sure? You sure now?
Yeah, I'm
Okay,
sure.
all right.
Because, you know,
Okay.
you can trip me up when you go 3, 2,
I'm not going to trip you up. I'm not trying to trick you. Now, 98 factorial starts with 98 and counts down.
Oh, 97. Okay.
Until it gets to 3, 2, 1. And now what do you see happening? Oh, well, that drop, everything drops except the what?
When you said 101, I'm so confused.
She meant 99.
Oh, so 99 what?
Did I say something? I must have said something wrong. Okay, it's
So
100.
what's the answer?
100 times 99.
Oh, okay.
And then if you'd like to pick up your calculator, I would not object.
Yeah, I'm gonna
You
do
can multiply that out. Would multiply it without using your calculator, right? In that 9900.
Mm-hmm.
Okay, so all right. Let me introduce Power Series for you guys, and then we'll come back and we'll start it again on Monday. Okay. Practice as many series as you can. Practice the stuff at the end of the section. And you might want to practice these problems on page 599. I'm going to write that down here. Go ahead and write it down. It's on page 599. Anything, let's see what I got here. Any of the problems, 7 through 29, anything, any odd problems on that page. Any of the odds. That'll give you lots of practice on finding out where these things converge or diverge. Okay, let me go back to something called power series. Fine. There it is right there. Okay. Now, so this is section 11.6, and I want to point out that until now we've been talking about series with constant terms. I mean, it might be like a half plus a fourth plus an eighth. They have constants, and we haven't seen any variables in them. But there are things called power series that have variables in them. If you look at that, and we say we're going to look at the sum from n equals 0 to infinity of x to the n. I don't know what x is. That's fine. I'll worry about it later. But if I let n be 0, x to the 0 will be 1. The next one is 1, so that'll be plus x to the first, plus x squared, plus x cubed, plus x to the nth. Okay, that's a series with a variable in it instead of specific numbers. Now, what we have now then is a sort of a generic series, and we might want to know, well, does it converge for some x's and not others, or what does it do? Well, if you look at this particular one, it looks like a geometric series, because how could you get from one term to the next, guys? If you start with, what's a going to be first of all?
1.
A is going to be 1, and you get to this next one by multiplying by x and x and x and x every time. So it's geometric with a equal 1 and r equal x. And you know what? We know the sum of remember the sum of a geometric series was a over 1 minus r? So the sum of this geometric series is 1 over 1 minus x. Now, that's interesting because, for example, there's a function, and what it's saying is that it has what we call a series representation. So, for instance, if I said to you on your calculator, figure out what 1 over 1 minus 0.3 is. All right, do that for me, guys. What's 1 over 1 minus 0.3? If we let x be 0.3.
0.7.
0.7? 1 over 0.7, which would be what? 1 divided by 0.7?
I think I did it wrong.
1.43.
All right, yeah.
Yeah.
1.43 if I round it off. 1.42857, something like that. So let me write that down here. 1.42 8571, blah, blah, blah. Now, I want to point out here that I let my r be something that's less than 1. And when does a geometric series converge?
When it's less than 1.
When the absolute value is less than 1. So what that's saying is that this series converges to that. In other words, this series right here, if I look down this series and I add things, for instance, if I let x be 0.3 and I didn't look at the rest of the series, I'd get 1.3. Well, you know, 1.3 is not quite that, but it's close. If I do the next one, it would be 0.3 squared. In other words, I'm looking at the sequence of partial sums here. Let's see what 1 plus 0.3 plus 0.3 squared is. That's 1.39. I'm getting closer to this. If I looked at the next one, it would be 0.3 cubed. The point here is, guys, the further I look down this series, the more it gets closer and closer to what the value of that is.
Wait, so it converges?
Yes, it converges to that. Remember
Wow.
0.6 and 0.66 and 0.666 got closer and closer to 2/3. Well, here's a function that we can write this series for, that if we go far enough out in the series, we get close to what that value is.
I'm
Okay?
confused.
If I went out to, hang on, if I went out to 10 here, it would get closer and closer to 1.428571. Okay? So I tell you what, one of the things I want you to do for homework is let's do that. We won't need to go to 10. Let's go to 7 and look at the sequence of partial sums. The first one will be 1. The next one will be 1.3. If you add the third one, what did we say it was? 1.39. 1.39. If we looked at the fourth power, I think it's going to be closer to that. I think it's going to be even closer to that. You can see that that sequence of partial sums is getting close to this value. That's what I mean by converging.
Oh,
Okay.
those are, I can't.
What?
Like, is it greater than 1? I'm so
The
confused.
0.3 is greater. I know it's going to converge because it's a geometric series with R. Here, because I picked R equal 0.3, that's less than 1. So I know this series is going to converge.
Oh, okay. I'm tripping. You good? I keep
Is it a good
looking at
trip
the
or a
one.
bad trip?
No, the 1.4. I was like, but that's the sum.
Yes, that's the sum. That's the sequence of partial sums. Now, guys, let me show you this. Suppose I picked R to be 5. Now, what do you know about a geometric series with R equal to 5?
Here come it diverges.
It diverges. Look at what you would get here. You get a 1, you get a 1 plus 5, you get a 1 plus 5 plus 5 squared. That thing is just getting bigger and bigger. It diverges. It diverges. Okay, little definition here. We'll talk a lot more about this next week, but it says let X be a variable. A power series in X is a series of the form an x to the n, which is equal to a0. If you start with 0, you can start with 1 or 0. There are reasons we start with 0, but we'll talk about that later. That'll be a0 plus a1x to the first, a2x squared, a3x cubed, all the way down, where ak is just a real number. There's just some real number here. If we let x take on a value, we have a series we can test with our other methods. So in other words, if x were a half, if I let x be a half, this thing would look like 1 plus a half plus a fourth plus an eighth. And what kind of series would that be again? Geometric, with r equal to a half, because every time you get from 1 to the next, you go a half. The sum of that would be 2. That's what the geometric series formula says. But so it converges for x equal a half because it's a geometric series with r equal to a half in that case.
So
On the other hand,
does
question?
that start at 0?
We'll start them at 0 mostly, yeah. Okay. It's nice to start them out with a constant. If on the other hand I let x be 3, look at what it would look like. It would look like a geometric series, but now you get from term to term by multiplying by 3. And then when you start adding those up, the sequence of partial sums is just getting bigger and bigger. It's divergent. So what we want to know is, for what values of x is this thing convergent? And for what values is it not convergent? What can I put in for x to make this convergent? Clearly anything that would make x or the absolute value of x less than 1. And there's a nice way to tell that. I'm gonna stop right there. All right, I'm gonna stop right there because I don't want to get into this right now because there's too much to say. Y'all have anything to say? You got 2 minutes to say it in. Anybody?
Oh, I'm tired.
You stayed up till 4 a.m.
Yeah, I was trying to get,
Okay.
do some research.
Okay, so I hope I gave you something that I did not waste your time today. What I want you to work on, and it's not 8 o'clock, so whatever. What I want you to work on is doing as many series from the stuff we've previously done as you can. And then we'll come back to this Monday morning and we'll start talking about power series again. Okay.
No quiz, right? No quiz.
You know what? I'm gonna do no quiz, but because what I want y'all to do is work hard on the homework and see if you have problems with it. But as soon as Monday comes, you're gonna get a quiz on all the stuff we've done about series. Okay.
Everything?
Well, I'd say, well, we've already done a couple of sections, couple of quizzes on that. So I don't know. Yeah, it can be anything. Okay. Anything from series that we've done.
Gotcha.
Okay.
Look at my flow chart. Look at the I put one other thing online. Hang on one second, guys. I forgot. I put this online. Let me see if I can find it. This is on Moodle, and I'm crazy about setting up review things here because this is a hard stuff to get your head around. But what I did was I outlined everything we need to know at this point. How do you generate sequences? How do you do them recursively? Know how to find the limit of a sequence. Then we got into series. A series converges if its sequence of partial sums converges. I did all that. I then talked about positive term series. You can mark this integral test off that. We did not do the integral test, so do not worry about that. I've suggested problems in the book for you to do. There's some suggested problems right there on these are just positive term series. I talked about the ratio test. Is she crying? And then I talked about absolute convergence and conditional convergence. There it is. Everything I've been doing for the last 2 weeks.
Oh, that's a great resource.
Thank you very much. I worked very hard on that, okay?
And thank you.
No, thank you.
I thank you.
Now, what you got to do for me is practice because I cannot give you experience. You have to get that on your own. Bye. Have a nice weekend.
All right.
Okay? Later.
Bye.
Oh, please.